This video is covering section 9.8, power series. Now, we've already talked about Taylor polynomials, so I said in class that a polynomial is a finite function. So now we're going to look at if I make that finite function go on for infinity. So when that happens, if I add infinite amount of terms, then we're coming into a series. So we have what, if we take that Taylor polynomial and we make that infinite terms, we can call that a Taylor series, or in general, we have what's called a power series. So not all power series are Taylor series, but every Taylor series is a power series, okay? So for example, we could find the Taylor polynomial for e to the x, and this is the fourth degree Taylor polynomial for e to the x, and so that's the polynomial, and obviously we said that the higher the degree of the polynomial, the better approximation. So what if I went to an infinite degree polynomial? Well, then that would be look like this here. So we have this ellipsis here. Now, that's really important to know that if it were to stop at this nth term, that would still be the nth degree polynomial, which is not a series because it's showing that it's stopping somewhere. So it's really important that we have those ellipses to show that this goes on and on for infinity. So now this is called a power series. So the definition of a power series is, we're going back to the notation, the sigma notation that we used in the first half of the chapter. So, and notice that instead of the series of a sub n, we now have an x involved. Okay, so because a power series is representing some function. All right, so think of a power series as a function of x, and then like the coefficient or what the term looks like is defined by that a sub n. All right. So again, just like with Taylor polynomials, we have centered at some c. So, and then we have the Maclaurin, which is centered at 0. So if you just have an x and it's not plus or minus anything, then think of that as like a center at 0. And then we can also have the power series centered at a different c value. So then you would have x minus c. Okay, so this first example is actually quite easy. All we're doing with this first example is just looking at and seeing where these power series are centered. So we have the series for part A, x to the nth over n factorial. So the center here would just be at 0 because you have the x. So this would just be a center at 0. Part B, you have x plus 1. So then the center would be minus 1. And then part C, you have x minus 2, so your center's at 2. Really is that simple for that first example. Okay, so now we're going to look at an actual power series and talk about, since we're talking about series again, remember in the first half of this unit we were talking about where series converge or diverge. So now we're going to look and talk about when a power series converges or diverges. So a power series centered at C will always do one of the following. And I just noticed that the notes that I gave you is actually missing this page. So right now, if you'll pause the video and go online, and I've posted this extra page online. So if you'll go, you can upload that, or you can just kind of write down what I'm about to do in your notes off to the side. Okay, so again, this page is not in your notes, but the page is uploaded online, so get that, and then we can follow along here. Okay, so a power series centered at some c will always do one of the following. First of all, it could converge at x equals c only. So that means that the power series, whatever function you have, wherever your center is, it will come to a finite number when you add up those numbers only at the center. Okay, so if you deviate from the center at all, then the series would no longer converge for other values of x. And we're going to see how this looks in just a second. So it could converge only at c and nowhere else. It could also converge a finite distance either way from the center. And when we have a finite distance from either direction, we call this the radius. So we're going to use capital R here. So if you have this center here, and you converge some finite distance away from the center, so we'll say this is R, and then also you have the same distance in the other direction, then you would have this is some x minus c, and this is some x plus c. So then it would converge from x minus c to x plus c. So if you think of this as kind of like an inequality, when you graphed inequalities in like middle school, think of this being the set between x minus c and x plus c. So everything shaded in blue is going to converge. Now, the points exactly at x minus c and x plus c, they're going to do something a little special, which we'll talk about later. Okay, and then finally we could have our series converging everywhere. So that means absolutely for all of x. So the number line here, again, if we have our center, is just going to be an infinite line. So it's going to go on and on forever and ever. Okay? All right, so again, when you have a power series will do one of the following. It will converge only at its center. It would converge some finite distance away from the center, therefore having a radius. And then it could converge everywhere. All right, so the number r, we said, is called the radius of convergence for the power series. Again, think of it as the distance from the center of the power series for which the series converges. If the series converges only at c, that is at the very beginning, that first example, then it does not converge for any distance away from c. Therefore, the radius of convergence is 0. If the series converges for all of x, so that would be the third example, then the radius of convergence is infinite. Okay? Then the set of all values for which the power series converges, so this would be for a finite distance away, so c minus the radius between c plus the radius is called the interval of convergence. And that makes me realize a mistake. Sorry, I'm doing this since the page is missing in my notes too. I'm kind of doing this off the cuff. So that made me realize that I did this wrong here. Sorry. This would be center minus the radius, and then center plus the radius. My bad. Okay, so hopefully that makes a little bit more sense now. All right, so to determine the convergence of a power series, so that's what we're going to be doing in this whole section, 9.8, is determining the radius of convergence of a power series. So we learned all those tests in the last series, or the last section, and we're going to be using exclusively the ratio test to find the radius of convergence for a power series. Okay, so we're not done with that first half of that chapter. Okay, so for our first real example, we're going to find the radius of convergence for this power series. Now, the reason you know it's a power series is because it's a function of x. Our other series for the first half of the unit did not have x involved, just the n, so that's how we know it's a power series. Okay, also, you would not be asked for a radius of convergence for any series but a power series. All right, so we're going to use the ratio, not ratio test to determine the values of x for which the series converges. So let's remember the ratio test. So the ratio test is you're finding the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Now recall that we're comparing this limit to 1. If the limit is less than 1, then the series converges. If it's greater than 1, it diverges, and if it's equal to 1, it's inconclusive. So we're going to do that for this example here. So we have the limit as n approaches infinity of 3 times x minus 2 to the nth power over, n plus 1 over 3 times x minus 2 to the nth. All right, now we're going to simplify this first before we move on. So, and remember that we're taking the limit as n approaches infinity, not as x approaches infinity. So then if we simplify this, the 3's are going to reduce to 1. And then we have x minus 2 to the n plus 1 over x minus 2 to the nth, leaving us with a lone x minus 2 to the first power. All right, so now the limit as n approaches infinity of x minus 2, n doesn't come into play at all now. The n has completely gone away. So if that variable has nothing to do with my expression, then this is just approaching x minus 2, and that should have the absolute value around it. Okay, so that's approaching x minus 2. Now, remember, we want to find where this series converges. Now, how do we know whether that's equal to 1 or not? Well, we can determine for what values of x make that less than 1. So remember, we want this to converge, so we want the absolute value of x minus 2 to be less than 1. All right, now, there's two values that do this because we want the absolute value of x minus 2 to be less than 1. So that means that x minus 2 is going to be between -1 and 1. Then when you solve, so that is add 2 everywhere, then you get 1 is less than x is less than 3. Okay, so that would be kind of like, not completely, because we're going to look at that in a minute, kind of like our interval of convergence. So our series is going to converge everywhere between 1 and 3. Okay, now, if I look at the center of the interval, so this is just kind of looking at the radius of convergence. If you look at the center of the interval we got in part A, so the center of 1 and 3, that's 2. And then if you look at where the series is centered, so back up here at the beginning, x minus 2, that's also centered at 2. That's how it should work out. Then, to find what we're finding is the radius of convergence here. So how far left and right can you go of the center and still converge? So if the center is 2, you can go to 1 or you can go to 3. That means I can deviate by 1. Therefore, the radius of convergence for this problem is 1. Okay, now for example 2, again, we're going to find the radius of convergence. So we need to use the ratio test. So the limit as n approaches infinity of the absolute value of n plus 1 factorial times x to the n plus 1 divided by n factorial times x to the nth. Simplify that down, and we're going to get n plus 1 in the numerator times x in the numerator. The denominator completely goes away. So now as n approaches infinity, not the x, n plus 1, infinity, plus 1 is infinity, times x. Doesn't matter what x is, this is going to approach infinity. Now, in number 1, we got an expression, x, of absolute value of x minus 2. So we could come up with the values for x at which this converges. However, in number 2, the x doesn't come into play anymore because the limit will always be infinity no matter what x is. So, since infinity is always greater than 1, then this power series will diverge everywhere, except, if you remember, a power series will always converge at its center. So if I diverge everywhere, that means all x except at its center, which in this case is 0. If you look here, that's just x. So the center is 0. So it's the only place where this converges. So for the radius of convergence, then, it's not infinity, and it's not 0 because x is 0. It's 0 because it diverges everywhere except at its center. Okay? All right, third example, find the radius of convergence of this series. And again, it's a power series because you see that x sitting there. All right, so we have the limit as n approaches infinity. Since we're taking the absolute value, we can ignore the negative 1 to the n. So this is going to be x to the 2n plus 1. When I replace the n with n plus 1, you're going to get 2n plus 2 plus 1, therefore 2n plus 3. So that would be the n plus 1 term. So it'll be x to the 2n plus 3 divided by 2n plus 3 again, factorial. Now, since my series is a fraction, I'm going to go multiply by the reciprocal of the original nth term, which would be 2n plus 1 factorial divided by x to the 2n plus 1. Okay, clean this up a little bit. So now we have, let's look at the x's. We have x to the 2n plus 3 divided by x to the 2n plus 1. So when I subtract those have a difference of 2. So you're going to be left with an x squared in the numerator. Then we have 2n plus 1 factorial over 2n plus 3 factorial. The bigger of those is 2n plus 3 factorial. So you're going to be left with 2n plus 3. Then the next term there would be 2n plus 2, then 2n plus 1 factorial, and those cancel. Okay, so now this is simplified. You don't want to go any farther than this because you can tell the degree there of n. Remember, we're looking at the limit as n approaches infinity. So the x squared in the numerator is not going to affect our limit. So as n approaches infinity, if you look at the degree of n in the numerator, there are no n's, so that's a degree of 0. Over the degree of n in the denominator that'd be n times n, so n squared. So this is a low degree over a high degree, and so if you get a low over high, then you get a limit of 0. Okay, so since our limit is 0, so again, 0 times x squared, doesn't matter what x squared is, you're always going to get 0. And when we compare to 1, 0 is always less than 1. So similarly to question number 2, this will converge for all x instead of diverge. Okay, so this converges for all x, so therefore our radius then would be infinity. So just to make sure, don't get it confused, because I know it can be confusing, because in part 2, we got infinity as our limit, but our radius was 0. And then for number 3, we got 0 as our limit, but infinity was our radius. So don't get that confused. Okay? Make sure you understand what you're saying when you're looking for the radius. Okay, I'm actually going to stop this video at this point. You still have another video to watch, but I'm going to stop at this point just so that you can have it split up a little bit more evenly for you. So the next video will cover talking more about intervals of convergence.